Okay, thank you everyone for tuning into this talk, which is about the paper towards optimal lower bounds for K-median and K-means coresets appearing, as I guess everyone who's tuning in is aware of, at this year's talk in 2022. This is joint work with Vincent, Cohen-Addad, Kasper Green Larsen, David Saulpic, and well, myself, who's Chris Schwiegelshohn, who's the one giving the lecture for today. So let me dive straight into it. What is the problem that we're looking at? The problem that we're facing today is the K clustering problem. And the K clustering problem consists of the following. We're given a set of points in some metric space. For example, could be the Euclidean plane. And along with a positive integer k and a positive integer z. And our objective consists now of finding a set of k centers such that the sum of z powers of distances of every point to its closest center is minimized. So as an example, for this particular point set and k equal 3, if we place the following 3 centers, then we would at least have a reasonably good clustering, at least with respect to some of these objectives. So you may ask, what is the role of Z here? Well, this just captures many popular clustering objectives from literature. For example, for Z equal 1, we're looking at the K-median problem. And this is just us trying to minimize, for instance, the average distance between the points and their assigned centers. Now, on the other extreme, you could also look at what happens if you let the limit of z go to infinity. And this leads to the k-center problem, where we want to minimize the maximum distance between any point and its assigned cluster. And we will not really look at distances or z's that are that high in power. So z going all the way to infinity is way too large for our purposes. So I want you to think of z essentially as being an arbitrary large constant, but still constant. And lastly, the arguably most popular objective of the bunch is the k-means objective, where z is just equal to 2. So in this case, we're aiming to minimize the sum of squared distances. And this is in particular, the objective that people like to look at if the points lie in Euclidean space. Okay. So we're not going to actually look at how to solve these problems or these combinatorial optimization objectives. What we're going to look at is just a question of how to store data set with respect to these objective functions, and also motivate like what a good storage would actually mean. So let's just take a look at this particular instance. So here we see, no matter how many centers we would like to throw at the problem, that there are kind of 4 well-defined clusterings in the data set. So it seems natural that we would like to have at least 1 point from every one of these clusters, right? So 1 from this group, from this group, from this group, and this group. And this stands in contrast to this point set, where there is no real identifiable structure. So it's not really, it was clear that we would need at least 4 points for the previous point set. Here we really, at least the eye test doesn't tell us that you could do a lot better or a lot worse than just storing 1 point. Now, this kind of thing, compression and storage of clusterings of points for with respect to clusterings, is captured under the Coreset paradigm. So let me explain what the Coreset paradigm actually is. We're given a set of points A, indicated here by the green points, and we want to find a weighted subset omega, and this point set omega is supposed to represent A in the sense that I'm going to define now. So what we want to do is show that the cost of omega as evaluated on any candidate solution S minus the cost of A as evaluated on the same candidate solution S is going to be less than epsilon times the cost of A on S. So as an example, if we say these 4 points here are the points of omega, and the weights here are indicated by the numerical numbers above these points. So for instance, this point here has a weight of 4, meaning this point here represents 4 other points. Then we want that this candidate set of centers, these 2 centers, if we evaluate the original point set on them, and if we evaluate the Coreset points on them, weighted by the number of points that they're supposed to represent, that the difference between these 2 costs is negligible. Now, a couple of remarks here are in order. So first off, the weights do not have to be integers. They can be anything. They just have to be non-negative. And while I did say that omega is a subset here, in Euclidean spaces, there may be some benefits to also requiring the points not to be subsets of the original input. For other metrics, this is usually the case, but for Euclidean spaces, we may be okay with just a subset of the Euclidean space and not a subset of the original point set. And lastly is that this guarantee here, that difference between Coreset point set and original point set is at most like this additive epsilon error. This has to apply for any candidate solution S. So in particular, it also has to apply to non-optimal ones, perhaps even rather stupid ones, such as this one right here. So for this set of points, we want Coreset point set and original point set to have roughly the same cost. Okay. So what do we want from a Coreset? Well, the most important characterizing feature of a Coreset is how few points it consists of. So if, generally speaking, if a Coreset consists of fewer points than all previous Coresets, and it's normally considered the better construction. Secondary objective is that you also should be able to compute the Coreset. This is usually given by most algorithms, though there are some exceptions to this. And as a tertiary objective, we would also like the algorithm or the analysis, ideally both, to be as simple as possible. Okay, and today we're mainly going to focus on this first part here. So we want to just understand a little bit better what the space complexity in terms of number of stored points for Coresets are. Give you an overview and idea as to what we've been able to achieve. That since the entire research community working on the Coreset problem, this here is the overview over the, well, let's say past 20 or so years on Coresets for Euclidean spaces with respect to the k-means and the k-median objective. And not going to walk through the entire set of related work. As you can see, it's quite vast, and I'm pretty sure I also forgot some people. What I really want to just focus on is this recent line of work initiated by Dan Feldman, Melanie Schmidt, and Christian Sola, who actually gave the first construction showing that Coreset sizes that were independent of both the ambient dimension D as well as number of input points n were possible, right? So they were the first to achieve essentially just a polynomial dependency in k and epsilon. It only applied to the k-means objective back then, but this has been now improved and slowly but surely whittled down to what is currently known as the state of the art, which is linear in k and small polynomial in terms of epsilon. So what is also known, Coresets have also been applied for other objectives such as finite metrics and doubling metrics. Finite metrics just mean any metric induced by a set of endpoints. And here, for both of these metrics, you can see that unlike for the Euclidean spaces, we have not been able to get rid of certain dependencies on these metrics. So for example, for finite metrics, you still have this log n dependency appearing in all constructions. And for doubling metrics, you still have a dependency on the doubling constant D. Now, the title of this paper was well, it had lower bounds in the title. So let me talk a little bit more about lower bounds, especially lower bounds for all of these problems. So if we just look at the Euclidean lower bounds, not too much is actually known. So for the K-median objective, in a recent paper, Baker, Braverman, Huang, Jiang, Krauthammer, and Wu showed that you need at least K times square root of epsilon minus 1 many points. And moreover, this lower bound, as far as I know, only applied to the K-median objective. Huang and Bishnoi, also in a recent STOC paper, showed that for higher powers of Z, well, some dependency, exponential dependency on Z is necessary, or a dependency on the ambient dimension D is necessary, one of the two. And what I want to draw attention towards here is that we do not actually know too much, right, in terms of lower bounds. So if you just look at what we know for K-means, the first lower bound gives us nothing because it only applies the K-median objective, and the second lower bound also does not give us too much because their Z is just equal to 2. So essentially it just says that you need omega of K points, which, well, that is an obvious lower bound. Okay, so if we just compare that to the aforementioned state-of-the-art upper bounds in Euclidean spaces, we see that, well, we are optimal, or at least close to optimal, in terms of the dependency on K, so we're off by this log K factor. In terms of the dependency on epsilon, there's still a polynomial gap for the case of K-median. And for the case of K-means, essentially not too much is known in terms of the correct dependency. Okay, so moving on to finite metric lower bounds, here we actually know a fair bit more. So Baker, Braverman, Huang, Jiang, Krauthammer, and Wu, in the same ICML paper, managed to show that an omega of K over epsilon log n lower bound exists for point sets in finite metrics. And this is very close to the upper bounds by Cohen-Addad, David Saulpic, and myself. So the only difference here between upper and lower bound is just epsilon to the minus 1 factor, at least with respect to the K-means and K-median objective. Okay, so now where do we come in? Well, we first and most important result, in my opinion, is that we present a lower bound of K times epsilon to the minus 2 many points for Euclidean spaces. Now, there's still a polynomial gap here between epsilon to the minus 2 and this dependency here, and I'll say a little bit more about that in just a moment. The other lower bound that we prove is a K times epsilon to the minus 2 log n lower bound for finite metrics, and indeed also for doubling metrics. So the same lower bound also applies to doubling metrics where you place log n with a doubling constant. And this essentially closes the problem for K-means and K-median. So for K-means and K-median, Z is equal to 1 or 2, right? And in this case, these two things are matching up to polylog factors. Okay. So the finite metric and doubling metric problems, at least with respect to medians and means, have been closed. So let's take a closer look at this Euclidean lower bound. So we didn't really know what it was worth, or at least what the dependency in terms of epsilon was worth, until we also managed to find the following upper bound, which says that you can also obtain a Coreset of size K times epsilon to the minus 2 times K, if you wish. So K squared times epsilon to the minus 2. Now, generally speaking, I would say that quadratic dependency on K is worse than a polynomial dependency on epsilon. But what is interesting about this is that this lower bound here has an optimal dependency in epsilon. And this is, well, the first Coreset construction that I'm aware of that achieves an optimal dependency in epsilon without depending on any other parameters. So without depending on epsilon, on log n or on d. So in that sense, we believe that this upper bound here gives some evidence to the fact that this lower bound will be the right answer. Okay, So to just summarize, what are the key takeaway messages here? The Coreset problem for k-means and k-median is now settled in finite and doubling metrics. And for Euclidean spaces, we have managed to show a lower bound of k times epsilon to the -2. This holds for k-means, k-median, any power of z, any constant power of z, I should say. And we also strongly believe, combined with our newly improved upper bound, that this lower bound is indeed going to be the right answer. Okay, so for the remainder of time that I have, I would just like to briefly give an idea as to how you can prove the lower bound for Euclidean spaces. So the theorem, the precise theorem is stated as follows. We want to prove that there exists a set of points in d-dimensional space such that any coreset of P must consist of at least omega of k times epsilon to the -2 points. In this case, coreset can be an arbitrary point set in R to the D with arbitrary non-negative weights. Now, the hard instance is quite simple, actually. So P is just going to be a d-dimensional simplex, so where D is of the appropriate dimension that we would like to prove, and or appropriate size that we would like to prove. And the candidate hard instances are just clusterings induced by unit norm centers. So this is the structure that we're going to look at. Now, in order to prove the theorem, you need to prove the following, or you follow the following 3 steps. So first step is to show that every clustering with unit norm centers of the original point set, so of the original simplex, has cost at least 2d minus some term that depends on square root of d times k. And complementing this, this lower bound on the cost, we have this upper bound on the cost of any coreset that we would be looking at. So if you want a t-point set, your designated coreset consisting of t points with arbitrary non-negative weights, then you can show that the cost will be at most 2d minus omega of square root of k over t times the weighted norms of P. So we would really like to relate these 2 terms, right? Because this is a coreset, we know that these 2 terms cannot be off by too much, and then we would just like to solve for t. And using the bounds on B and K, we would just like to infer that P should ideally just be of the same order as D, which is K over epsilon squared. Okay, now the thing that is preventing us from doing this is this weighted sum over here. So what we need to do is control that somehow. And the way that we're going to do this is by proving that if omega is a coreset, then we can show that this weighted sum is some constant or d divided by some constant. So if you've proved these 3 steps, then you know by the coreset guarantee that the difference between these 2 is at most some epsilon times d, and then you just solve for t, and that gives you the desired bound. Okay, so let me wrap things up. Again, our main results is in terms of lower bounds, and for finite metrics and doubling metrics, these lower bounds are optimal, at least with respect to k-means and k-median. And for Euclidean spaces, we also believe that they're optimal, given that we now managed to also prove an upper bound that has an optimal dependency in epsilon, or the same dependency in epsilon as our lower bound gives us. Now, what are some interesting open problems? Well, the obvious open problem is that is just to solve the coreset complexity for k-means and k-median in Euclidean spaces. So can you just match this lower bound? And to leave you with one less obvious, but for me very interesting open problem, is what happens for higher powers of z, specifically z being 3, 4, some moderately large constant. So far we know nothing about an optimal dependency in K that does not also have a dependency of epsilon to the minus z, at least. And what would be really nice is to separate the dependency. We know that some exponential dependency in Z is necessary due to the lower bound of full inhibition, but we would really like to prove that dependency epsilon to the minus O of 1 would be possible. So I'm not even asking for anything optimal in terms of epsilon, just something that is independent of Z. And I guess with that, my time is up. Thank you for your attention.